Okay, welcome to the lab. So today we're going to go into the lab 5, which is we're going to start to use some applications in the S051 microcontroller with the software simulator. Okay, before we start, we go through some introductions of these microcontrollers. So a microcontroller basically a chip, just like IC. It consists of some peripherals or some functions which is listed in here. So there are 8-bit register, 8-bit microcontroller. So the data bus is also 8-bit only. They only send out, only can transfer 8 bits of data at mods at one time. Okay. Then for the address bus, they have a 16-bit, so means they have the 16-bit of address bus, but only have 8 bits of data bus. Then they have the on-chip RAM and ROM. So the ROM is for them to store the permanent programs. So when you load the program in, they are permanently stored there. Okay. The RAM is for you to run the program executions. Then they will have a 4 8-bit bidirectional input and output ports. So this is the thing you're going to use the most in your lab. In your lab, you're going to use input output pin. So there's a 4 ports. Every port have 8 pins. So they have 8 pins from 0 up to 7. So let's say there's a port 1. Then you have port 1 0 up to port 1 7. So there's 4 ports. That you have a port 4 0 up to port 4 7 also. Oh, sorry, it's 3 only. 0 1 2 3. Okay. Port 0, port 1, port 2, and port 3, the name given. So the input output means you are able to send out data by using the pin and also get the data by using the pin into your microcontroller, either sending out data from a microcontroller or sending in data into your microcontroller. Apart from that, they're also able to using the UART, which is serial communications. Okay. So this is serial communication, means they are using single line or few less line to transmit data. If it's a parallel, means if I want to send out 8 bits of data, I can using 8 pin to send out the data. But in a serial, maybe they just need 2 pin only to send out the data. For UART, there's only 2 pins, or the RX and TX. So TX means transmit, RX means receive. So the TX is the one to transmit the data out, then RX the one to receive the data in. So if I'm sending out 8 bits, I'm only using 1 line only. But if it's parallel, means I'm using 8 lines to send out all the 8 bits of data. So there's a difference between serial and a parallel. Then in the microcontroller, they also have some timers which help you to count the timing. Okay, it's just like the counter you built before in the labs. Okay, they are able to count the do some counting. Then by using the clock, they are able to do some timing program. Okay. So in this is the simplified structures of the microcontrollers. They have 8 kilobyte of in-system programmable flash memory. So the flash memory means they are permanent and they are also programmable. You can change the program inside this memory, but after you power off, the program will still inside here. So this is one of the important part of your microcontrollers. Every microcontroller, they should have the flash memory to store the program written by the user and loaded into the microcontroller. Even though you power off the controller, the program should still exist store inside in your microcontroller. So this is the technology they're using, the flash memory to store the data. Then they have a 256 byte of internal RAM. RAM is just like the RAM in your PC to help you to do some program executions. But they are not permanent. When you power off, the data inside RAM will be lost. And then they have the timer, the 3 16-bit timers or counters, and they have interrupt functions. So interrupt function is just interrupt control. So let's say you are running a program, you are at your main program here. So you are running an instruction from line 0 to line 100. Maybe in this program there's 100 line of instruction need to execute. So when you go up to line 30, you're running the instruction here. So suddenly there's the signal sending into your micro. So let's say this is your microcontroller. There's a signal sending in, which is the interrupt signal sent into your interrupt pin of your microcontroller. Then they will stop the execution in this line here. After they finish the line 30, after they execute the instructions, they will go and entertain the instruction. So they will go jump to the interrupt routine, interrupt subroutine, and run the program here. Okay, maybe something very important you need to run first instead of doing the main program. Okay, this is the function of the interrupts. So you can send an interrupt signal to ask them, hey, I want you to run certain more high priority program. So after sending the instructions, then they will come to here and run this code. Okay, after they finish run the instruction, then only they will go back to where you stopped just now. So they will go to line 31 to execute the next instruction. Just now you stop at 30, right? After you finish 30, you come to subroutine. Then you run the subroutine at the end. Then you go back to line 31 to continue back your main program. So this is one of the functions of the interrupts in the microcontroller. Then they also have the UART port for serial communications. So they also have the watchdog timer. Watchdog timer is something like your timer, but the watchdog timer is for the program executions. So this is the 4 IO port we mentioned. So each one is 8 bits. Total you have 32 lines. Okay, then EEPROM memory is also a permanent memory where you can store some permanent data, which is very important in that. Then the SPI is also a serial communications. Okay, then this is just the oscillator to give you the clock pulse. So just like your flip-flops, you need to have a clock pulse, only your flip-flop will respond. So the way they build the microcontroller also using those flip-flops method. So that's why you need the oscillator to make sure the whole IC is working. So this is the pin layout of the microcontroller. As you can see, this is the port 1. So when they mention port 1.0 means the bit 0 of port 1. So port 1 is 8 bits of data. So this is bit 0, 1, 2, 3, 4, 5, 6 up to 7. So when they mention P10, they refer to this bit. When they mention P13, they refer to this bit. If they mention P17, they refer to this bit. So if you are sending data to this port 1 pin 0, then in your IC, so let's say this is the register for port 1. It's the one in here, this one. So if I send a 1 into this pin, then they will store a logic 1 at your bit 0 of this register. Okay, so this is how they're sending data into your microcontroller. Okay, then if you send a 0 to the second pin, then they will store a 0 at here. So how you're going to send 1 or 0 is the same method as what you did in the flip-flops. So if this microcontroller is using 5 volts, so if you want to give a 1, then we need to give them a 5 volt power supply. If it's a 0, then we need to give a 0 volt power supply. So this is how you are giving them the logic 1 or 0. So in the other way, if you want to use the port as the output, as a programmer, we can write the values into this register also. So let's say I want them to giving out certain values. I can give them a 0, 0, 0, 0, then 1, 0, 0, 1. So if I define it by using my assembly programs with setting port 1 to these values, if it's an output, then I go and detect it. I can getting so let's say this is port 3. I change to port 3. So I'm using this port. So if let's say this is the values, then my port 3 will giving out a voltage value which is 5 volt. Since I'm setting the value is 1 0 0 1, then 0 0 0, right? So 4 0. So this will be giving 5 volt. Then the second pin, when I detect, is giving 0 volt. This is also giving 0 volt. Then this is giving another 5 volt. So this is functions of the input-output port, and this is the way you're giving out the power from the microcontroller. So if I connect this thing to a resistor, then go to the positive side of a LED, then go to the ground, then this LED will be lights on. But if I connect this thing to a LED, it won't light on because I'm giving a 0 here. So this is the pin layout of the microcontroller, and if you look at it, there's total 4 port, right? And most of the pins will have more than one functions. So for example, if you see port 3, bit 0 and bit 1, they also is working for RX and TX, which is for the serial communications. So most of the time, one of the microcontroller, they will have more than one functions. Okay, so this is the pin layout, which is total 40 pins for this 8051 IC. Then we go to the next one. We look into the memory organizations of this microcontroller. They were divided into two types. One is called the program memory, and then the other one is called the data memory. So the program memory is basically helping you to store all the programs you written by you, then you'll store in the ROM. So it will permanently and store in your microcontroller, even though it's the power of the microcontroller. Then the data memory is the locations for you to execute your program to store a temporary data. Then the program memory have two parts. One is called flash technology, one is called EEPROM. Both are also a permanent memory. Even though you power off, the data will still be inside. Then in your 8051, they have 8 GB of ROM and 256 byte of RAM. Then they also have the capability to extend the maximum of 64 kilobyte of memory, because they have a 16-bit of addressing capability. If you're 16-bit, then you can point it to 2 power of 16 locations. So that's why a 2 power of 16 is equals to 64K, which is 64 times 1024 here. So they can access to this much of locations. The function of address is to pointing to the memory. So let's say this is a memory. So let's say I only have 2-bit address. Okay, I have 2 bits only. My address bar is only 2 bits. So it's 2 power of 2 equals to 4 locations. I can only pointing to these 4 locations. So if I'm using address 00, then I'm pointing to this location. If I'm using 01, I'm pointing to this second locations. If it's 10, I'm pointing to here, and it's 11, I'm pointing to here. Same go to the 2 power of 16. You can start with all 0 until all is equal to 1. You are able to pointing to this much of locations. Okay, but the built-in one is only this much of RAM and ROM. So you won't use all the 16-bit unless you're using the extended external memory for this microcontroller. They have these functions to do the extension of memory. Okay. Then here is the memory map of your microcontroller. If you they will have a 128. Okay, this is a 128. 3 locations for you to use. Put any values. Then the address map is from a 00 up to a 7F. The next one is the special function register. Special function register, we'll look into it in the next sections. After this, basically they are also resistor, but they have a specific functions. They are not just empty resistor for you to storing values. They are a special, they have the function just like the port 1 resistor we discussed just now. They are basically controlling the values to your port 1 pin. So that's why we call it as a special function resistor. They are not general purpose resistor for you to store any random values. They have their own function. So this is this location for you to store from address number 80 to FF. Then another one to F3 locations, they are using the same address numbers, but they have a different addressing mode. So by using direct, you will access this area. If using indirect and you give using this address number, you are going to access another 128 free locations. Okay, so this is how they design these microcontrollers. By doing so, they are only using one register only for you to access the whole memory match, which is 8 bits only, because the address number is only from 00 up to FF, right? So you only have 8 bits of locations to access. Then 2 power of 8, you will have a 256 location can point to only. So that's why you have a 256 location which in your RAM here. So you can using this to pointing to all the locations you want by using 8 bits address pointing. Okay, so this the next one we come to the special function resistor, the SFR we are talking about just now. This is some of the special function resistor of your microcontroller. So some of them are using for like this is for IO port, right? The port 0, port 1, port 2, and this should be port 3. So there's 4 ports for you to sending out data and getting in data, the one we discussed just now. Then some is using for interrupts. So you need to setting some control of the interrupts. Then some is for setting all those serial communication. So all this special function resistor is just like a configuration setting for your microcontroller. So let's say I want a serial communications operate at 50 kilohertz. Then I need to setting some values in this register. So let's say I want to sending out define the size of the data to send out, let's say 8 bits or how many bits. I also can define in this serial communication register. So all these are the special function register functions. How to use that register or how you set the values, you can refer to their data sheets. Then they will tell you what kind of setting will give you what kind of response. Okay, they are just same as the normal register. They will have a storage for you to store values. So let's say if I put 1010, I'm going to doing 50 kilohertz serials. Then in front is a 1010 also. Then it will sending out the serial bit 8 bits. So this is an example how you setting it. Okay, we can using the special function register to configure how we want to using our microcontroller. So in this lab, we will do this programming code to work on the port 1 as an output. Okay, we were going to use this program. So as usual, you start with the origin at 00, then the A jump to main. Okay, this is the common one. Then they will start to this line. Or if you didn't use this, A jump should be okay also, because they will straight away knows that this is the main coding here. So the next line will come after your ORG. They will come to this line here. Okay, so basically this one is just equals your P1 equals to 00. So they're equaling your P1 to 00 values. So mean your port 1 register will all become 0. 8 bit of your port 1 become all 0. So this is the way to define as an output port. If you want it to be an input port, you can set it to 1111, 1111. So all is using as input. You also have the options to define pin by pin. You have a P10 up to P17 here. So you can define any pin you want to work it as input or output. So let's say I want the pin 7 as input, I can put 1 here, pin 6 as input, also 5 as input, then 4 I want it as output, I put 0, 3 output, 2 output, 1 input, 0 output. I can put it in this way. I can set this value to my port 1. So if this one I need to change it to 1111 is 13, so is equal to D, right? So I put D2 here. So I change this to D2, then I will configure it as this way. This 4 pin as an input, this 4 pin as an output. So you can define pin by pin. In here they're using all the port 1 as a output, so that's why they put P1 equals to 0, 0. Then they come to the starting, they define they put this one, P1 equals to 1, right? Then this another one, they equal your P1 equals to 2. Then they jump start, go back to the start, they keep on looping and doing this thing. So if it's 1 means your port 1 becomes 0, 0, 0, 0, 0, 1. And port 1 becomes 0, 0, 0, 0, 0, 0, 1, 0. This is equals to 1 and this is equal to 2. So this is the program doing. So basically they keep on changing these two values, become 1, 2, 1, 2, 1, 2, 1, 2, here repeating. Okay, why they do so is they relate this program to this circuitry. So if you look at it, you are changing the values of your port 1, 0 and port 1, 1. Okay, these two values keep on changing. The other remain the same as 0. Okay, so that's why they're doing some connection in your port 1 bit 0 and port 1 bit 1 here, right? So your port 1, this two pin is connected to LED. So this is a 5 volt, connect to the positive of LED. Okay, then the negative side connect to your port. After the resistor, connect to your pin 0 and pin 1. So let's say if you want the LED to be on, the negative side should connect to ground. So that's why you need to give a 0 volt here. If you give a 5 volt, then there's a potential difference, the same 5 volt, so this one will be off, and this one is on. So if you as discussed before, if you give a 1 here, then you will give 5 volt, you give a 0 here, you will give a 0 volt. So now the program is 0, 0, 0, 0, 0, 0, 0, 1. Right, then the next one is change to 0, 0, 1, 0. So initially it is 0, 1, so this is giving you a 5 volt and this is giving you a 0 volt, right? So this one will be off first, then this one will be on, right? Then they change the value to a 0, 1, so this one becomes 0 volt, this one becomes 5 volt, then this is become off and this become on back. So they are actually changing blinking the LED on and off by using this program. So if you are using this program in the simulator, yes, you can see the LED blinking. But if you are really looked into the hardware implementations, you won't see it blinking. This is because the program running is very fast. You are using a microcontroller, they are operating and running the coding at maybe megahertz or gigahertz. So in this microcontroller, they're running the code very fast. So I mean they change the value 01 to 02, 02 back to 01 in very fast speed. So in our human eye, we cannot see the changes happen. So at the end, we won't see the on off happen. You may see just LED keep on lighting on or off, it depends on the circuitry. So you won't see the on and off effect. So what you need to do in real application, in real applications, you need to add a delay. So this is what they do. This is 2 delay they added in. This part is the same. They equal your P1 equals to 0, 1. So this is the coding for you to on your D2 and off your D1, right? Then they call a delay. So a delay, it's just like a wait So they wait for 1 second or a certain amount of time, 2 seconds or 0.5 seconds, so that your eye can see the LED is on and off. The LED 2 is off and LED 1 is off. Your eye can see the thing happen. Then only they change the value to this one, where your D2 is off. Okay, you off your D2 and then you on back your D1. Then you see, yeah, they change from on to off and off to on. These two already changed the state because there is a wait time in between. Then before you change it back, you still need to call another delay also. So that's why you need to have a wait also at here. Then only you look back to on it back again. So that's why this is the exact coding required for you to do the experiment in the hardware implementations. So if you look at it, this is a call, means they will call something. Where is it? It's located at this delay. So they will come to this delay here. So in this delay, they are moving something into your R1. So your R1 register is just an empty register to store the value. So it's equal to FF here. So it means all bit equals to 1 here. Then the next line is move R2 equals to values F0. 1 1 1 1 0 0 0 0. Okay, then they come to this line, DJ inject means decrease. Then they will jump if not equal to 0. So they will decrease the values at this R2 register. So your R2 will decrease by 1. Every time they will decrease by 1. So it become 1 1 1 0 1 1 1 1. They are minus 1. After they do the decrement, they will check whether this value is equal to 0 or not. If it's not equal to 0, not 0, they will jump. The J, they will jump if it's not 0. Where they jump? They will jump to the thing you label here. So I put it delay 2, so means they will come back to this delay 2 and do the minus again. So it do the minus again, then this one become 1 1 1 0, your R2. Then they will do the same thing, checking again whether it's equal to 0, then it's not. They will keep on looping in here, keep on minus 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 until your R2 become all 0. Okay, then they won't jump anymore. They will go to the next line. They do the same to your R1. Okay, reduce my R1 by 1. Then they will jump to delay 1. Since it's after reduce 1, they are not equal to 0, they will jump to delay 1. Okay, when they jump to delay 1, they will start again your R2 with these values. Then they continue to reduce R2 again. After finish, they go to reduce R1 again. So this is basically a while loops, a 2 while loops. So let's say x equal to 1000 here. Okay, then x minus minus here until your x is equal to 0. Then only they will jump out of these while loops. Okay, so they are using this thing to consume your processing time, so that you do something nothing here, so you create the wait time here. Okay, so this is how they're doing delay in assembly language. Okay, so for this lab, and I remember when you call a delay, they will come to here after they finish. Then they finish everything already. Then they will come to return. Then they will return to the next line from where you call. I call it here, then they return back to the next line here. Okay. So basically, this is this is the thing you're going to do in your lab simulations. The one you can run is only this one. If you want to try this one, it may take a long time for you to start at this coding here. So what you can try, if you want to try, you can do is you reduce these values. You can reduce it instead of FF, you put maybe 0.08 for both, or 0.5. You try to put any value and see how long they will start in here. But I think should be fine if you put reduce on the numbers of this delay. Then in this program, you need to have a submission in this lab where you're required to program a binary counter from a 00 to FF. In the flip-flop lab, it's only 2 bits. So in here is 8 bits hexa number. So you can using the 8 LED in the simulations to display out the changes from 00 up to FF. Okay. Then you submit your assembly code with the explanations as the one in here. This is a comment. You just put a comment at your code so that we know what are you doing. So that is all the thing to submit, and yeah, you need to submit a short video to show the changing of this 0, 0. It's not just necessary for the full up to FF. Just showing a few changes also can. Okay, we just want to see it actually is doing the counting, starting to change. Okay, maybe 5 to 10 seconds to see the sequence is correct together with your code for the submissions. Okay, so I think that's all for this lab. Yeah.